Welcome to this explainer. Today, we're diving into something absolutely mind-bending. What happens when the perfect, symmetrical world of ancient Greek geometry crashes headfirst into the incredibly complex, cutting-edge realm of quantum mechanics? We're talking about a mashup of two disciplines separated by thousands of years, brought together by researchers José Latour and Germain Sierra. And honestly, the results are pretty incredible.
So, how exactly does ancient geometry meet quantum mechanics? I know, it sounds literally like the plot of a sci-fi movie, but physicists are actually using shapes described by Plato millennia ago, specifically the Dodecahedron, to solve some of the most complex quantum information puzzles we face today. They're basically mapping the absolute fundamental behaviors of the universe directly onto classical geometric structures. Crazy, right?
Now, don't panic about the quantum physics. We've got a clear roadmap for this explainer. We'll start with the quantum geometry puzzle, then mapping quantum entanglement, move into the quest for perfect states, and hit our climax with building Platonic states. After that, we'll uncover the prime connection and finally wrap up with shaping the quantum future. Let's get into it.
Section 1. The quantum geometry puzzle and distributing multipartite entanglement.
You see, the core challenge in quantum systems is figuring out exactly how entanglement is distributed across many different parts. That's the absolute key to understanding how these wild systems behave. But what I absolutely love about this research is the tone. The physicists approach this highly technical mathematical problem with a real sense of playfulness. They basically treated complex quantum states like geometric building blocks, just having fun with the math.
Section 2. Mapping quantum entanglement and introducing tensor networks.
To understand how these quantum puzzle pieces fit together, we've got to look at how scientists currently map out this entanglement. Enter tensor networks. Think of them as adaptive blueprints. The source material describes them as a bona fide method to exploit the actual complexity of a quantum state. Basically, they give us a super economical way to represent how different parts of a quantum system are connected and correlated to one another, traditionally adapting to whatever geometry the system dictates.
Section 3. Quest for perfect states and the incredible power of absolutely maximally entangled states. Now let's open up the next layer of this metaphorical Russian doll. We need the perfect tool to use inside those tensor network blueprints we just talked about. We're talking about absolutely maximally entangled states, or AME states for short. These are actually quite literally called perfect states. They're the ultimate puzzle pieces because of one really unique property. Their reduced density matrices are proportional to the identity. Okay, in plain English, no matter how you slice these states in half, the two halves remain perfectly, flawlessly entangled.
But here is the kicker. Finding these perfect AME states is notoriously difficult. There's a really strict mathematical roadblock. For instance, the math works out perfectly for 5 or 6 qubits, but say you try to find an AME state for 4 qubits, or maybe 7 qubits with a local dimension of 5. It is mathematically impossible. They simply do not exist. No way around it.
Section 4. Building Platonic states, which brings us to the visual climax of quantum geometry.
So the researchers started wondering, what if we take these multipartite states and arrange them not on some boring standard grid, but on the geometry of a Platonic solid? They came up with a very specific recipe. Step 1. Grab a dodecahedron, that 3D shape with 12 pentagon faces. Step 2. Paste a perfect 5-qubit AME state onto every single one of those 12 pentagonal faces. And step 3. Link them all together by defining the physical indices right at the corners, the vertices, where those faces meet.
And the result is what they call a Platonic state. It's incredibly elegant. The physical qubits act as the anchor points, sitting right on the 20 vertices of the dodecahedron. Meanwhile, the ancillary degrees of freedom, which are basically the underlying quantum connections derived from those 5-qubit AME states, they live right on the pentagon faces. It's a stunning way to represent a highly complex quantum tensor network.
If we focus right in on a single vertex of that dodecahedron, we can see how this actually works physically. Right at the corner, 3 different pentagons meet. Each one brings an ancillary index from its own perfect state, and the researchers set up a strict agreement clause here. The physical index, the final state of the qubit, only takes the value of the ancilla when all 3 of them match perfectly. If they don't agree, it just drops to 0. This clever little rule weaves the entire 3D structure together flawlessly.
Now, if you take that 3D dodecahedron and flatten it all the way out into a 2D map, you can easily track all 20 vertices. And mapping it out like this isn't just a fun exercise. It allows physicists to calculate the massive amount of entanglement this unique structure holds. They analyze the entropy across a bunch of different partitions on this flattened map just to see exactly how efficient this geometry truly is at holding quantum information. And the result of that calculation? Staggering. When they tested a massive non-local split, 10 spins against the other 10 spins across this geometric shape, the von Neumann entropy hit a maximum integer value of 10. Okay, why does that matter? In quantum physics, hitting that absolute mathematical ceiling means this Platonic state distributes entanglement with incredible efficiency. The geometry perfectly maximizes the quantum correlations, a total game changer.
Section 5. The Prime Connection, Exploring Mathematical Coincidences in the Platonic Solids. As if mapping quantum entanglement onto ancient shapes wasn't cool enough, consider this unbelievable pattern. Think about the properties of every single Platonic solid. The tetrahedron, it has 4 faces. Well, 4 is the prime number 3 plus 1. The hexahedron has 12 edges. 12 is the prime number 11 plus 1. The octahedron, 6 vertices. That's 5 plus 1. It is a literal mathematical coincidence. For every single Platonic solid, the number of faces, edges, or vertices always exactly equals a prime number plus 1.
So why does prime plus 1 matter at all? Because it perfectly aligns with something called Reed-Solomon codes. These are classical error-correcting codes, first developed way back in 1960. They're used to build fully AME states, but they have a catch. They specifically require a prime number of dimensions plus 1 site. Because all Platonic solids naturally follow this exact mathematical rule, every single one of them perfectly accepts AME states based on classical Reed-Solomon error correction. The ancient math literally perfectly aligns with the quantum math. You just can't make this stuff up.
Section 6. Shaping the Quantum Future, and looking at why all of this actually matters.
Ultimately, these Platonic states are way more than just a playful thought experiment. They give physicists a completely novel architectural blueprint. They prove, without a doubt, that complex, multipartite entanglement can be deployed with extreme efficiency. And by seamlessly connecting classical error correction, like those Reed-Solomon codes, with quantum topology, researchers now have a fundamentally new way to think about building and scaling quantum systems, totally bypassing the traditional constraints of regular lattices.
Which leads us with a really provocative thought to wrap up this explainer. We just saw how the absolute most complex building blocks of quantum entanglement perfectly map onto the classical ancient geometry of Platonic solids. If a 12-sided dodecahedron is the perfect vessel for a 5-qubit quantum state, what other universal shapes are just waiting out there to be discovered? What other ancient geometries are secretly the blueprints for the quantum universe?